Hey guys, this is just a quick video to explain how polarity works. So, first thing you want to know is that a polar molecule is a molecule with a positive side and a negative side. And we're going to say it's a partially positive side because it's not like an ion. It hasn't completely lost an electron, but it is charged somewhat. Okay, so water is a very important polar molecule. You should come out of chemistry knowing that water is polar. So we're going to draw a picture of water. It's a bent molecule. It's got lone pairs up here. And the oxygen side of water is a little bit negatively charged. So to show that it's not entirely negatively charged, but partially charged, we do this little kind of curvy D. It's a Greek letter delta with a negative. And the hydrogen side is actually positive. So we do another little Greek letter D plus. So the oxygen side is partially negative. The hydrogen side is partially positive. Okay, that's a polar molecule. Another, like a biology type term for polar molecules is hydrophilic. So like molecules that mix with water, including water, are polar. Nonpolar molecules are molecules that do not have charges. So there are lots of polar molecules and lots of nonpolar molecules. A simple example of a nonpolar molecule is carbon tetrachloride. That's carbon with 4 chlorines around it. And I'm not going to draw any charges on it because it's nonpolar, so there are no charges on it. And just so you know, this applies only to covalent molecules. Covalent molecules can be either polar or nonpolar. They're one or the other. This doesn't apply to ionic or metallic compounds. They're a different thing. Okay, so we're going to now talk about what types of molecules are attracted to what other types of molecules. So polar molecules are attracted to or will mix with other polar molecules. So for example, water is polar and alcohol is polar, so they mix. Water is not attracted to nonpolar molecules. So for example, oil is nonpolar, and so this is why oil and water do not mix, because oil is nonpolar and it won't mix with the polar water. Now, if we're talking about nonpolar molecules, they will mix with other nonpolar molecules. So, for example, nonpolar oil, and all oils are nonpolar. So, oil will mix with something else that's nonpolar, like butter or shortening. But oil will not mix with anything that's polar. So, like water or alcohol. It doesn't mix with alcohol really well either. Okay. So that's important to know. Another thing that is important to know is that the symmetry of a molecule can kind of help you figure out whether it's polar or nonpolar. So polar molecules are not symmetric. And nonpolar molecules are symmetric. And this gets kind of confusing because nonpolar is symmetric. Now, if you look at this carbon tetrachloride, this nonpolar molecule, see how if I cut it this way, it's symmetric, same on both sides. If I cut it this way, it's also symmetric, same on both sides. I want you to think about cutting it along the bonds to figure out if it's symmetric or not. Now, water, it does look symmetric this way, so sometimes people want to be like, oh, it's symmetric. But think about cutting it along the bond. Think about cutting it this way. You can see on this side there's an H, on this side there isn't, so it's not symmetric. So that means it is polar. All right, so we're going to do a bunch of examples of this now, and this is the last thing we're going to do in the notes, just figuring out if these molecules are polar. We're also going to figure out what shape they are, just to review shape. So this is carbon dioxide. It is linear. because there's no lone pairs on the center atom. If I cut it this way, it's symmetric. If I were to cut it this way, it's symmetric. So it's nonpolar. This is sulfur dioxide. The double bond doesn't matter for polarity. So if I cut it this way, it's symmetric. However, if I cut it this way, it's like water. It's not symmetric across this diagonal line along the bond. So it's going to be polar. And the shape, of course, if you've got two bonds and a lone pair, is bent. Okay, and we just did water. Water is bent, and we said it's polar because it's not symmetric along that diagonal. Now this one doesn't have any lone pairs, so it's another linear molecule. But this one has an H here and an N here. So if I cut it this way, it's not symmetric. So it's actually going to be polar as well. All right, now let's do some with 3 bonds. So we've got 3 bonds here and no lone pairs. If that happens, that shape is called trigonal planar. Again, I know you guys already learned this. We're just reviewing here. Now this one's a little bit tricky. What I want you to think about is cutting it across each of these 3 bonds. If I cut it this way, see how it's symmetric? If I cut it this way, see how it's also symmetric? And if I cut it this way, it's also symmetric, right? So that actually makes this one nonpolar. It's symmetric all those 3 directions. Now this one, this is 3 bonds with a lone pair, which we call trigonal pyramidal or pyramidal. See how if I cut it this way, it's symmetric, but if I cut it along the horizontal, it's not. There's an H down here, but not one up here. So that makes it polar. Now this one is another trigonal planar because we got 3 bonds with no lone pairs on the center. Hopefully you're getting to the point where you can just recognize these shapes pretty easily. Now if I cut it this way, it's symmetric because I've got H's on both sides. But if I cut it this way, it's not symmetric. Now the double bond doesn't matter, but the fact that this is an O and this is an H, that makes it not symmetric. So this one is polar. Okay, let's do some with 4 bonds. Remember, anytime it's got 4 bonds, it's going to be tetrahedral. And this one's right here, it's symmetric. If I cut it this way, it's the same. If I cut it this way, it's the same. So it's going to be nonpolar because each of these atoms is an H, so they're all the same. Now this one is tetrahedral. There's nothing written in the middle. That actually is a carbon. When they write it like that, that means carbon. You know, it's kind of weird. Still tetrahedral though. And then if I cut it this way, see how there's a Cl over here but an F over here? That makes it not symmetric. So that means this one actually is polar. All right, so hopefully that makes sense. Several different concepts here. Polar molecules have a positive and a negative side. Nonpolar don't. Polar molecules mix with other polar molecules, but not with nonpolar molecules. Polar molecules are not symmetric, and nonpolar molecules are. Now, this symmetry is related to the charge. These might seem like 2 separate things about polar and nonpolar, but in order to have charges, you have to be not symmetric. If you're symmetric, all of the charges will cancel out, we'll find out. But if the molecule isn't symmetric, then one side can be negative and one side can be positive. And we'll talk more about that next time. But that's all you need to know. Have a good day.